conference will now be recorded.
So, am I audible?
Yes.
Before starting the session, I would like to understand the background of audience. So, you are all from working industry professionals, or are you like students, or what is the background? Quickly, I mean, I can just introduce yourself. Alasia, we can start from you.
Uh, I'm studying BTech fourth year, sir. EC domain. So I
Okay.
just wanted to explore uh, more into embedded systems or VLSI. So I just thought of attending this demo so that I can choose
Mhm.
which would be flexible for me.
Okay. Okay. What about others? Prasad and Praveena.
Sir, I'm pursuing my electrical engineering. Last year, I'm
Mhm. Okay. Okay. Anyone from the industry background? Okay. So to start with, I mean, we more talk about embedded systems and IoT things, right? So what is embedded systems? I mean, my first question is to you. So I mean, let's keep this whole session more interactive. So I mean, it's not something like I just deliver and you'll be in the. I generally like, I don't like the radio mode of delivery. So I just, it should be kind of discussion based session. So to start with, I just want to understand what is your understanding about embedded system. We hear a lot about embedded systems, VLSI, IoT, networks. So, but in that context, like, what is embedded system is? What is your understanding about embedded system? Arivarasu, what do you know about embedded system? According to you, what is embedded system?
From my point of view, embedded system is about making a technology, new technology by using Arduinos and sensors like this.
Okay. Praveena?
So in my point of view, embedded system is we work on both hardware and software. So and then like we work on microcontroller processor like sensors, and then IoT like booting process like that. Um,
Okay.
yeah.
Okay. Any other answers?
Uh, it is a it is like my having microprocess based system which implements uh, electrical or mechanical implementation.
Yeah. So ideally, an embedded system is something uh, you consider anything which has software and hardware, right? It's a combination of hardware and software, right? So any system which has hard a combination of hardware and software. So can you give me some examples, like let's say a simple agrotech application where I need to have some kind of irrigation control, let's say. So I need to have some kind of software stack which should be running, right? So let's say control application, some kind of cloud processing. I need to connect to internet. Also, there is a need of some kind of hardware into it, right? So when I say hardware, is it limited to only electrical hardware, or what else I can have? When I say about system, apart from electrical hardware or electronic hardware, what other hardware, what other kind of hardware I can have when I talk about embedded system? a mechanical hardware, right? So like I need to have, let's say, in irrigation system, I need to have some valves, solenoid valves. I need to have. I need to have some kind of electrical systems. Uh, it's a combination of, I can say. I mean, when I say about combination of software and hardware, the hardware is not limited to electrical hardware or electronic hardware, right? So generally, I mean, in some of the universities like IITs and NITs, they have something called electronic system design, a concept of electronic system design. So whenever we are an embedded engineer, we need to understand the entire system of it, right? So we are designing a system. So let me consider any simple electronic system. Maybe can you give me some project ideas like what you might have seen, real-time project ideas or real-time product? Can you give me one embedded product example so we can start with that discussion? So we can hold on to that embedded product and we can see that like what are the things we need to learn, right? So then based on that, I will be telling you that like what we will be learning as a part of this course. Okay, so let's consider that product, any product. Can you give me one product which will fascinate you? I mean, like favorite product, embedded product, which you are interested in. You can take any product. Can you just give me some products? It can be consumer electronics, defense, space tech, anything. Take one product. Can you give me one product example? Any product. Prasad, can you give me one example of any product?
Sir, they might be alarms like smoke detector alarms and fire detector alarms.
Yeah, let me consider fire alarms. Okay, so in fire alarm, what are the things? Let's say like okay, consider an example of fire alarm. So can you tell me what are all the things we need to? If I say like I want to detect, implement one fire alarm, so what are the things I need to know? Consider an example of fire alarm.
It should detect if any fire is there, and it should respond accordingly.
Correct. Right. So what are the systems? What are the components? Let's first identify the components. So see, this is the project idea, right? So generally, any embedded system, we start with one project idea. So if someone asks you to design a fire alarm, so what question do you ask to the customer? So let's say like now uh, Prasad is a customer who is asking me to design fire alarm. So will I directly jump into design fire alarm, or like will I ask some questions to him? Like what questions do I ask him? Like when I say that, when he say that like he wants up a fire alarm. You will ask like the specifications, right? So we start with the specification. So what kind of fire alarm he wants, and whether it has to be like industrial grade fire alarm, or whether he wants to fit that fire alarm into his apartments, or this fire alarm is sitting somewhere in the forest to detect the forest fire, right? First, any design, when you consider, I start with the specification, right? I have to start with the specification. I need to know what kind of fire alarm I am designing, right? So let's say if he say that like I want to design fire alarm which will sit in my apartment, which is sitting in my apartment. So given that specification, right? So now what are all the things I need to decide?
We need to check voltage, power, like and temperature.
Those
Sensor.
are actually specifications, right? You have voltage, power. Those are specification. In the specification, you will say that like what kind of power adapter you are going to give. So you can
Yeah.
say input power, right? Input power, and what is the maximum temperature you want to identify, or temperature condition. Whether see, whenever you are implementing or designing this particular temperature, not temperature sensor, it's basically fire alarm. So you also need to know that like where you are going to put this, where your apartment is located. So let's say like if your apartment is located somewhere in colder area, like let's say in Himachal or some other locations, your system should support those negative temperatures, right? Or let's say if your system is sitting somewhere in Hyderabad or Bangalore, still if your system, if it is capable of handling around 11 to 12 degrees Celsius, still it is okay, right? So you need to understand what is the specification you are going to address, right? So that is one of the important thing you have to understand. So once your specification is identified, then what next? So you should start identifying the components. So one important thing as embedded engineers, right? So many a times what people will do is like as embedded engineering, they study some kind of software aspect of it. Like they'll be studying just embedded C and some microcontroller programming, or some embedded drivers, device driver aspects. Is it really sufficient for you? As an embedded engineer, right? So you should be knowing a system. When I talk about system, you should be knowing how the components are manufactured, how your PCB is designed, how to read the data sheet of the component, right? How exactly you are interfacing, or what are the various voltage levels, how to debug a system, right? So these are the basic understanding we should know. Then only we will be a successful embedded engineer, right? So first thing, like as a system, what you're going to develop, the embedded system, so we need to understand various components which are required for designing these embedded systems, right? So can you tell me what is the first component you will identify in this system?
Gas leakage sensor or fire alarm sensor.
Yeah, fire sensor, I can say sensor, right? So sensor aspect. First I need sensor which identifies fire with all specification, right? So this is one of the example, but whenever you design any embedded system, this is, as I said, like with this example, we will identify various things what we will be studying. So when I say this is one of the example where I am identifying a fire sensor, what are the different sensors I may have to study as an embedded engineer? So let's say like if you are designing wearable sensor, so do you agree your smartwatch is also kind of embedded system?
Yes.
So if your smartwatch is an embedded system, what kind of different sensors you will be using in that? You need to have some variable sensors like your heart rate monitor. You need to monitor your body temperature, your sleep rate, right? Various parameters you need to identify, right? So same way you may have to go for like let's say you want to identify the speed of the vehicle. So which sensor you're going to use? Speed of the vehicle, which sensor generally it will be used? Hall effect sensors, right?
Axiomatic.
Hall sensors, speedometer, right? So now you have pressure sensors, which is required for monitoring the pressure of the tires, right? So that is also, you have seen that in the latest cars, you will be seeing what is the pressure of the vehicle, pressure of the tires of the vehicles, right? So you need to understand pressure sensor, right? So various sensors we will be studying. So we have to study various sensors. Now, this sensor output, what kind of output we will be getting from the sensor? what kind of output we get from the sensor? Is it analog? Is it digital?
Digital.
It can be digital or it can be analog. When I say my output is analog, it will be in terms of voltages, right? So let's say if there is a fire alarm, if I want to detect the fire, so your output voltage may vary, like it may be like by default it may be 0.3 volt. Suddenly if the fire is detected, it may go somewhere like 0.7, 0.8 volt. If there is a high probability of fire, then it may go up to 3.3 volt, right? But if I feed this directly to microcontroller or microprocessor or microcontroller, will I be able to read this data directly? Whether my microprocessor or microcontroller capable of reading this data?
No.
Okay, because my microprocessor or microcontroller is a digital in nature.
Yes. Yes.
So now if I want to read this analog data in a microprocessor or microcontroller and take some action, what I have to do?
We need to convert that analog data to digital.
Yeah. So what do I use there?
Gate to
Like
convert.
Right. I have to use analog to digital converters. Right. So now this analog data, either it will be in the parallel interface and it will be giving us bits, or it will be serial interface. And if my sensor is digital, how do I interface this digital data into microprocessor? So one way I can go with parallel data. When I say parallel data, if I want to transmit 10110, how do I transmit this data? I directly send through 5 lines. 10110. But what is the disadvantage with this kind of transmission?
we need more hardware pins.
We need more pins.
Hmm.
So to overcome that challenge, what I'll be doing?
We use serial
We have to go for
serial.
serial communication protocol. Serial communication protocol. So these serial communication protocols includes I2C. Have you heard about I2C? SPI. And if you are going for automotive application, you have to understand CAN. If you are going for aerospace application, you have to understand ARINC. If you are going for military application, you have to understand MIL 1553B, MIL protocol. So depends on applications, we have to study various interfaces. Okay. We discussed we have to start with what? We have to start with
Specification.
understanding the specification. How do we decide specification? Then we go for component identification. In the component identification, it includes sensors, actuators, what kind of microcontroller you have to use, right? Then once you identify these components, you have to start focusing on different interfaces. Okay. So the third part of the lectures, we will be studying about various, not in this lecture, as a course. Third part, we will be studying about various interfaces and like how to program, design these interfaces. Okay, so just give me a minute. Yeah, so basically I had sensor. I decided interface. Also, in case if it is analog, I need data converters. We need to study data converters. And once data converters is done, next I have to interface to microcontroller or microprocessors. So can you give me various examples, different types of microcontrollers, what you know? Different microcontrollers, what you have studied, different architectures of microcontrollers.
Risks is Von Neumann hardware.
Yes, those are the various architectures, right? Apart from that, like, have you also heard about, yeah, RISC and CISC you have heard, right? Using that,
8051
yes, x86,
exit.
RISC-V, ARM processors, right? These are the different architectures which you might have already studied, right?
Yes.
So we will be studying different architectures, x86, ARM architecture, RISC-V. Also, we will be taking practical boards like STM32 based boards, STM32 based hardware, and we will be doing some practical experiments in terms of interfaces, like how to access these sensors. And I talked about various interfaces: CAN, LIN, UART, I2C, SPI. So all the interfaces we'll be testing on this STM32 board. And we will be also talking about architecture of microcontroller, microprocessor, ARM processor, and we will be exploring various tool chains. How do you program these microcontroller with respect to embedded C program, or how do you use Cube IDE to program STM32, or you'll be learning about Keel compilers, how you can use these Keel compilers to program this microcontroller or microprocessor, right? So what are the different tool chains you have come across? Which are the tool chains you have used in your curriculum?
Keel we have used.
Keel you have used, okay. So whatever the compilers or techniques you have used, it is a bare metal technique, right? What do you mean by bare metal?
There won't be any OS operating system.
There is no operating system involved in it, right? So you
Yeah.
use a simple embedded C to program these controllers or processors. So that is what you might have studied in your BTech or PG. But when we deal with the complex systems, we need to have proper threading, proper process management, right? So if I want to have a multi-core processing, process management, threading, so what do I use instead of bare metal? Instead of simple C program, what do you use when you want multiple processors has to be running parallelly?
IDE, we use IDE.
That is for compilation, right? So that comes under toolchain, right? Like a cube IDE or Keel, that comes under IDE. But in the processor, I am talking about, not in the design side.
Okay.
We have to go for real-time operating systems or embedded operating systems, right? For multi-threading, right?
Yes,
So can you
yes.
give me some of the examples of real-time operating systems or embedded operating systems?
Free RTOS.
FreeRTOS. Zephyr, have you heard about?
No.
So there is another operating system called Zephyr. So which is extensively, it's a tiny um, operating system which will be capable of running on top of embedded computers or embedded processors. So we will be discussing, and we also look into some of the real-time examples how you will be running this Zephyr on top of a processor or microcontroller, right? So then when I talk about operating system, hmm, now you consider your laptop itself. It has a operating system in it, right? So how does it know how to talk to your USB driver or USB, or how it knows how to talk to mouse or how to talk to various peripherals?
Drivers.
We have to write the device driver. So that is one of the, like if you look into the LinkedIn, so you see that like in the embedded domain there is lot of demand in terms of development of these
Drivers.
device drivers. So that is one of the major thing what you have to learn in detail. So we will be extensively discussing for the same thing what we had done in the bare metal. So initially we studied like how to interface an I2C or how to interface a SPI, how to interface these CAN, LIN. So now we will come to the point that like how I can implement that on top of device driver. So we'll take Zephyr as an example, and based on that, we will be discussing various techniques. Again,
Okay.
we also take. I mean, Zephyr is a tiny OS operating system, but there could be a scenario where actual Linux will be running on the single board computers. Like if I talk about single board computer, can you give me some examples of single board computers?
BeagleBone.
Yes, BeagleBone, Raspberry Pi. So Arduino has come up with new single board computers. If you are closely following embedded hardwares, Qualcomm has come up with one nice hardware. Can you just tell me like which is that hardware? Samsung Q. Have you heard about it? Qualcomm based, Qualcomm and Arduino came up with single board computer, right? Qualcomm Q, they say. So that we will be discussing. I mean, basically we will see like how we will be running actual operating system on Raspberry Pi or one single board computing. and how we can develop these device drivers. We'll be discussing about how to uh, uh, build our device tree, how we can actually write a driver for it, how do we create our own application on top of operating system, various synchronization, deadlock issues, right? We'll be in detail discussing about various techniques for handling those things. Okay. So once we understand the device drivers, then we also see, like we talked about sensors. Along with these sensors, as a part of component, we'll also have actuators. So now it is not, see, now actuators also plays a major role in your embedded design, because see, actual actuators is not just a simple motor driver applications, right? When I talk about actuators, it comes buzzer, motor driver, or people will talk about what else? Any actuators, right? So like it's speaker. So
Release.
ideally, driving of this actuator is a all new concept. You know that like all ADAS or electrical vehicles, which kind of motor does it have? Is it a simple single phase motor, or what kind of motor does it have in ADAS application, electrical vehicles? Have you ever heard about BLDC motors, brushless DC motors? So ideally, designing these drivers, BLDC motors, right, or any synchronous motors, we need to understand how do we design these drivers, how do we drive these. So it has a lot of potential in the EV sector, right? So we need to understand like how these motors are driven, how we have to write a driver for driving these motors, the software drivers for driving these motors. If you learn those, right, so you have a huge potential in companies like Ola Electric, Ether, and many new electrical companies are entering to the market. So you need to understand this. This is a need of our, right? So we will be learning how we can design our drivers for these kind of actuators, right? So now, so far, whatever we discussed, this is the software point of view, all right? So just by learning the software, these softwares, will you be a qualified embedded engineers? If not, what is lacking? What is important thing you need to know?
Embedded C.
Embedded C will come in the bare metal itself, right? You have studied embedded C for programming aspect.
Execution and designing.
Execution also comes in the software side, right? I mean, like these are all software side. I mean, we planned, we understood the specification, we identified the component, we written the software now, right? So
Hardware things.
right, we need to understand how the hardware is designed. So as an embedded engineer, I don't say that like you will be designing the hardware, but you should know, let's say like now you have to interface from a sensor to your processor. Okay, sensor to processor, you interfaced. Okay, and now if your sensor is not talking to the processor, you are say if you are seeing some issue with respect to these interfaces. So what could be the possible issues? I mean, how do you resolve that? Let's say like now microcontroller, you know, sensor, you know, you have interfaced, like basically hardware engineer, he interfaced. Now sensor, whenever you try to read this sensor is not reading. So how do you debug this scenario? What are the possible steps you will be taking to do this?
We need to check whether that hardware supports that particular sensor.
When I say it supports, I mean, first thing, what do you do? See, when I say you have given a board, okay, which has fire sensor, and you have given a microcontroller. So now somebody asks you to write a program to interface this fire sensor to your microcontroller. So do you straight away start programming this?
We
Or
check pins
you have to
by knowing
understand,
the pins.
correct, you have to understand it is connected to which pin, right?
Data.
So how do you identify it is connected to which pin?
We have to refer the data sheet.
In the data sheet, microcontroller, with respect to microcontroller, they will give that, like which are the pins are available. But when you have a hardware, built hardware, you may not know, it is connected to which pin, right? So it is a hardware, it's a PCB which is already built. So now how do you identify where it is connected?
The schematic design of the board.
Right. We have to look into the schematics, complete circuitry, right? So let's say, like, I'll give you one example. Like, I'll just show you one of the schematic. So this is one of the schematic of STM32, right? So let's say, like, you have various interfaces. Now, if you consider this particular pin, you have connected your fire sensor to PB12, PB13, let me assume, right? So you have to search where this PB12 is connected to your processor. So you can see it is connected to STM32 PB12, right? So I need to understand where exactly these things are connected, right? So to understand that, first we need to know how to read this schematic, right? How to read this schematic. Based on that, we have to identify where it is connected, and could be like one is pin information you have to understand. But now let's say I have a scenario, you understood it is connected to which pin, but still your design is not working, you are not able to read the data. So how do you debug this now? First you looked into pin. Now if the pin is also not working, what could be the other possible issue?
The
Voltage
supply to the
level.
system. Yeah.
Yes, voltage levels, right? So you have to see your sensor may be expecting 3.3 volt. Your microcontroller may be operating at 1.8 volt. You have to understand various voltage levels at which it is operating, right? So in order to look into that, where I have to look actually, along with the schematic, we also know how to read these data sheets. Reading the, as the embedded engineering, reading the data sheet itself is a skill, because Is it for only voltage level I read the data sheet? For what else I have to read the data sheet? Let's say like you have given me the sensor. So are you reading the voltage level, or like are you reading the data sheet only to understand the voltage levels, or anything else you will be seeing in the data sheets? What else other information will be there in the data sheet?
Functionality also will be there, how it works and all.
Functionality, and even apart from functionality, the programming informations. Let's say like you have a communication between your processor and sensor. So there will be I2C, SPI. I agree, but along with that, you also need to know what kind of protocols, what kind of sequence you have to follow. First, you may have to send the register address. You may have to read the data, right? So those sequence of information, the sequence of data through and forth, that is very much needed, right? So those understanding how to read the data sheet, based on the data sheet, how to extract the information and write the device driver, or write my own uh, software code, understanding of that we'll be discussing in our uh, like maybe eighth or ninth session of the ninth uh, lesson or chapter of the embedded systems. Okay, so that will be mostly the hardware point of view. If someone as an embedded engineer, what hardware aspect we need to know, right? How to debug. So see, just embedded engineers we may not be able to succeed. The skill of debugging is very much important. I'll give you one example from like almost a week. Like as an embedded engineer, I'm debugging one important thing. So like basically there is a one programming cable which is not communicating. So as an embedded engineer, if you do not know how to check it in hardware, so we have to like just say like connect it. It is not communicating. You will replace the driver, then done. Your debugging is done. You will not be able to appreciate like how to debug. Now what I'm doing, I'm measuring the impedance across various lines. I'm measuring what is the voltage levels available. I'm seeing whether impedance matching is done. Is there any signal integrity issue? Whether my STM is responding? Is there any status bits which is communicating? So for after every stage of debugging, you should be like clear what I need to check to make sure or identify the issue. So identifying the issue and tackling the issue itself is a skill set, because everybody who know software, C program, embedded C, they can claim them as an embedded engineer. But just now the programming aspect, any artificial intelligence tool can do. I mean, if you just tell that like write a blinking LED, or not even a blinking LED, if you ask it to write a complex algorithm, ChatGPT saying that like these are the pins what I have connected the sensor, and write an algorithm to implement a particular scenario, then it is going to do. I mean, you need not much struggle to implement that, right? But now as an embedded engineer, if you want to survive in the market, the skill of debugging, the art of implementing these embedded systems is very much needed, right? So those skills we'll be learning in 8th or 9th chapter of this course. Okay, so then apart from this, we also need to know some of the standards, DO standards, aerospace standards, in terms of code quality, linting. Those aspects we will be discussing in detail. Then finally, once these aspects are done, right, so we will be going with uh, various aspects in terms of like IoT, right? So various IoT protocols are there. How do you implement these IoT systems, right? So those system aspects also we have to look into. Like I mean, at the end. So now we will be like initially whatever the discussion we do, those are with respect to the system, the detailed embedded system, or like I can say these discussions will be revolving around microcontroller or microprocessor, right? Once all these discussions are done, let's say like you understood like how to debug in the hardware. Now with this embedded hardware and embedded system, how do I build the complex system? It can be cloud interface, it can be IoT interface, how I can actually go with MQTT interface. Let's say on top of this existing operating system, how I can add one tiny ML model and run my own artificial intelligence systems, right? So those concepts we'll be discussing at the end. And finally, we will be trying to implement at least 4 problem statements. I mean, parallelly, we'll be working on different problem statements also. Final problem statements, it will be like each of 15 days, and one with the major problem statement, which are actually, I mean, I run a startup basically. So uh, I have various problem statements which are given by customers itself. Uh, I have space tech problem statement. I have defense problem statements, communication problem statements. So you'll be start working on those problem statements also. Okay. This is the overall plan. So can someone summarize? Like we started with identifying the actuators. We started with the system specification, then actuators. Then we will be discussing about interfaces. What are the different interfaces? CAN, LIN, MIL 1553B, ARINC, I2C, SPI, UART, Ethernet. All these interfaces we'll be discussing. We'll be discussing about data converters, like how do you interface ADC, DAC, pulse width modulations. And then we will start discussing about various controllers and architecture, x86, ARM, or RISC-V. What are the difference between these architectures? And we'll take STM32 as a example board. So we'll be giving boards from institutes where you can experiment various peripherals on this based on this architecture. So in that, while studying about that architecture, we'll also see like how you program to those architectures. So it will be starting with the embedded C. Then also we'll be discussing about a complex device driver. So we'll be installing Zephyr OS, and on top of Zephyr OS, we will be seeing like how do you design different device drivers, how do you, and we take some single board computers like Raspberry Pi. Then you will be starting discussing about uh, different drivers which you can build on top of these single board computers itself, right? Then we talk about actuators. When I talk about actuators, basically we discuss about the motor drivers which are required for current EV industry, and it has a huge demand in terms of EV industry. It will be mainly we'll be discussing about how do you design your own BLDC motor driver, how do you design your own synchronous motor drivers. So all these aspects we'll be discussing. Then we'll be starting discussing about tool chains and hardware aspects of it, right? So we'll be discussing about how do you design, not about schematic. I mean, maybe like very brief manner. We will be teaching with the KiCad like how you can design the schematic and PCB. But most of our focus will be like how do you understand this schematic? How do you uh, like decide what kind of microcontrollers you want? Or how do you identify what issue is? How do you debug these systems, right? So these aspects we'll be discussing in details. So then once that is done, then we start discussing about various debugging techniques, tool chains, quality aspects. Then we go for system level designing using IoTs, right? So like maybe MQTT protocol connecting to the cloud, running a tiny ML model on top of these embedded systems. Then once that aspects are done, finally we will be building our own projects based on my problem statements what I have. It's an industrial problem statements, and we'll be building the entire system. So my objective is like this course what you take, so that shouldn't be just like for job seeking purpose. So whatever the product you bring it out of it. So you need to productize also. I mean, like from government now, lot of grants are available to build your own products. You can see like Nidhi Prayas, which is offering around 10 lakhs of grant. You have something called Next Elevate from Karnataka government, which is offering around 1 crore to build the product. So instead of going for like 3 to 4 lakhs of job, so you can start building your own products and you can start giving the jobs, right? So my objective, like at the end of this course, you should be able to build your own product and you should start building your own hardwares and commercialize that. So that is a potential now. So the government is offering a lot of incentives to productize and hardware startups. So that aspects also we'll discuss. I'll give you some ideas because since I have my own startup, so I'll give you like how you can productize and commercialize the things what you build. So many things what we build in college, that will be just a college product, right? But college project, but ideally lot of projects has a commercial uh, uh, viability or commercial possibility with little bit touch of commercialization aspect. So something you have to do on top of that, but technologically you might have proved already, right? So those things also we can discuss how you can achieve that. Okay, so that is about overall course aspect. Okay, so if you have any questions you can ask me. Briefly we can touch upon microcontroller architecture and embedded architecture also in next half an hour. But before that, like with respect to course, if you have any questions or queries, you can ask. Any questions?
Sir, are we going to build any, uh, I mean, you said like you will be giving one problem statement, right? Like
Yes.
from scratch, we will be doing any kind of project like that, or how it is?
Yes, complete from the scratch you will be building the project. So if you are interested, if you want to build your own hardware, on that aspect also we can guide, because we have all the fabrication setup, assembly setup. So from that point, if you want to productize and take it to that project to that level, we can guide that way also. Or like let's say on existing hardware, we have various hardware platforms. On top of that, if you want to build anything on that end also, I can guide you. So but it will be like actual product based problem statements I'll be giving you, so which has a commercialization potential. So those problem statement you will be implementing or building.
Okay.
Any questions? We'll just take 2-3 minutes for question and answer, then I'll continue a little bit on architectural point of view.
Sir, like class timings are daily at this time only.
Class timings you can check with the institute once, so they will be scheduling the sessions.
Sir, will we get recorded sessions of this class?
Yes, you will get a recorded session of this class. Also, you will get the hardware. Okay, you will get one
Oh,
hardware.
okay.
That's what I said. Like, I mean, this is not just theory sessions. What you will be learning. So you will get one hardware. On top of that hardware, you have to build the systems.
Sir, difference between VLSI and embedded.
See, in VLSI, what you do, like, so here, which is the chip we are having, we are using. I mean, I said like which chip I'll be using. I said STM32. With respect to STM32, I'll be discussing, I mentioned, right? So here, whatever I discuss, already the chip is existing, right? So I'll not talk about how do you create this STM32 IC itself, right? So that is not my objective. But when I talk about VLSI, my objective is not to build the system, right? This is an embedded system in the sense actual product. My idea is not to build the product itself. My idea is to build that STM32 chips, ICs. So my innovation stops at IC level itself. At that, till that point, I'll be doing from specification of that IC till the STM32 IC, and you will be delivering to embedded system guy. So the embedded system guy will take that IC and he will build system on top of that IC. So if you are interested on Verilog, VHDL, digital design, then VLSI is suitable for you. If you are interested in building a system, when you want to see like something as a product, when you want to build, right? Or when you are interested more on software coding, operating systems, right? And PCB level component exploration, right? So then embedded system is a good thing for you. See, you don't always choose based on the job perspective, right? So whichever is passionate, I mean, whichever inspires you, whichever like having, I mean, whichever you feel that like it gives you pleasure when you execute those, right? So those field you choose, I mean, you'll be really successful in that field. So all the fields has equal potential and equal demand, but passionately in and out you should be knowing.
Okay, sir. Thank you.
Any other questions? Okay. So now maybe like as a first session, we shall start discussing a little bit about fundamentals of uh, embedded systems, and we also let's discuss some fundamental about various architectural point of view. It is a very basic thing what we'll be discussing. This is generic definition of embedded system, right? Somebody said like when I talk about embedded system, it is a combination of hardware and software which is integrated, right? So, and when I say hardware and software which is embedded together, right? So where this software will be running? So the software will be running on top of any computer, right? So do you agree 8051 is also a computer? 8086 also microcontroller is also a computer. Anything which has a computational capability is a computer, right? So ideally, when I say embedded system, there is like two aspects of it. One is processing and controlling. Okay. So can you give me one example with respect to any embedded system? What is processing and what is controlling? We were discussing about fire alarm, right? So in the fire alarm, what is the processing I am doing? What is the controlling I am doing?
Sensors is the process and controller controls it.
Sensor is the sensing, right? Basically, process is basically I'll be comparing the data of that sensor with respect to some threshold value to decide whether my fire is detected or not, right? So that is a processing part, the computational part. Then what I'm controlling? I'm controlling some kind of fire alarm, right? If in case like I have automated fire extinguisher, so I may be giving some control signal to that fire extinguisher, right? these parts are ideally a controlling application, right? So anything which has to do that, it should have some kind of intelligence, right? So when I say intelligence, some comparison in terms of addition, subtraction, multiplication, division, some program or software should be running on top of that controller, right? So that is where any system, when you see a computer on it, then you call it as embedded system. If I have something like a embedded a toy which has a simple microcontroller, do you tell it as an embedded system? If I have a toy, RF toy, you have seen that, like remote control toy, is it an embedded system?
Yes.
Yes, it is an embedded system, right? It has some kind of processing, right? You have to see like which direction it has to do. It has to control the motor direction, motor drivers. So these systems are embedded systems itself. Okay. So when I talk about embedded systems, there are general purpose systems also. If I consider Raspberry Pi itself is a embedded system. Is it embedded system? Or using Raspberry Pi, I have to build some embedded system.
Using that, we have to build some system.
Right. So it's not itself is not an embedded system. It is a single board computer. On top of this single board computer, you have to build the embedded system, right? So when I talk about embedded system, it is application specific. It is serving some application. When you have a smartwatch, it gives you time and also it senses your health conditions, right? When I talk about earphone is also embedded system, right? So it has some kind of Bluetooth, it has a control system, it will be receiving the voice, then it will be removing some kind of noise. So it is also kind of embedded system, and it is designed as a headphone application. So it is a specific application and real time and reliable. It See, when I say that like a embedded system, it should be a reliable system. Like I cannot have an indefinite meaning for that, right? So when I say that like I have a ADAS is also embedded system, which is highly complex embedded system. Now I cannot say that like I have put it into auto drive mode, and you cannot say that like it may succeed, right? When I say I have an embedded system, it should be highly reliable, and you should be clear that it will succeed 100% sure that like that system will work in this particular manner only. There shouldn't be some random or predictable models. Okay. And the system should be low power and resource efficient. Can you tell me why do we need system of low power? And in what scenario it should be highly low power? Can you give me some scenarios if the system is not low power, what will happen?
It may get damage.
No, it won't damage. I mean, it is consuming more power, but it is not in terms of damage. So there is one more important aspect for it.
Battery life should come.
Yeah, right. So actually, you assume your mobile processor is consuming a lot of power, and if your mobile battery dries every half an hour, will you like to take that mobile phone? No, right? So it should be ultra low power. The same way, you assume that like you have launched one satellite, if it is consuming a lot of power, so how satellite will be running? I mean, how satellite powers are, from where it is coming for satellites? From solar, right?
Solar.
Solar powered. So there, half of the day it doesn't have any solar lights to it, right? So there will be a complete dark time for that. And let's say like if completely battery drains from the solar and complete communication system will be lost, right? I mean, because continuous maneuver will be happening from the ground station. I mean, if the communication from the ground station is lost, you're completely losing the control of that. And let's say like some soldier is carrying some navigation device, and like he'll be like in the field for like few days, and if he's holding that navigation device and if it is drains in within a day or so, then he'll not be able to track, right? So it should be highly low power and resource efficient, and it should be fast, right? So your microcontroller, let's say if you are using microcontroller for fire alarm, and if the fire detection itself is taking around 5 to 6 seconds, so by the time your fire would have went to uncontrollable manner, right? So you should have a proper low power, resource efficient, and high speed system. That is our objective. Whenever you write a code, you should think that like how my code is going to run on the processor, and you should be clock cycle aware of the code. Every cycle of the code, right? You should be knowing like how many clock cycle it is taking to execute. If it is taking more clock cycle, you should know how to optimize that clock. That is very much important. Clear? Any questions in this slide? In terms of embedded system, when I talk about evolution of embedded system, let me consider ARM itself, because ARM is one of the most popular microprocessor and controller which we'll be using in industry. So ARM M series, right? M0, it was actually lowest cost, low area. It is traditionally used for your microcontroller application. Okay. Then M0 plus, it is like a size of around, see, like the first one was 90 micrometer, then size of coin. Then basically M3, it has IoT embedded kind of like application. So M4 has a DSP application. M7 has high performance computation applications, right? So depending on this is M series, same way ARM has A series and different series are there. Okay, depending on the application, I'll be choosing that particular architecture. So here we'll be mostly looking into STM32 architecture, and it is your assignment to find out what architecture it falls under. Is it M3, M2, M4, M7? Identify as a homework. Okay. So it started, early microcontrollers started with 8051 or 8086 or PIC. Those were 8-bit microcontroller. Okay. Then ARM is basically the next generation of the microcontroller. It actually 16 or 32-bit microcontrollers. One basic question I have. So architecturally, 8051 or ARM, is it the same architecture or different processor architecture? If it is different, what architecture it has? What M architecture has, and what uh, 8051, is it a RISC or CISC? It's a CISC architecture, right? In your BTech, you might have studied. What about what is the CISC full form? Complex instruction set architecture or computer.
Computers.
Another is RISC, right? What do you mean by RISC?
Reduce instruction set computer.
Correct. Reduced instruction set computers, right? So reduced instruction set, what is the difference between these two architecture? Anyway, like I mean, in the courses we'll have detailed discussion on this, but what is the basic difference?
CISC has more instructions and risk has a little bit less compared to CISC.
Correct. But in that scenario also, what is the um, difference in the hardware point of view? What is the difference?
Like instruction is less in risk, sir.
So in
Instruction
this
is less,
means
but hardware wise, so basically when I say less number of instructions, ideally it has less hardware, right? So when I have like more number of instructions, ideally it has more hardware. So which is power optimal now? Risk is power optimal or CISC is power optimal?
Risk, sir.
Ideally, risk is power optimal because it has less number of
Instructions.
right?
Yes,
Whereas
sir.
CISC has more number of instructions. But now, when I say less number of instructions, how will I be able to achieve same? Can I run same code in both risk and CISC? Same code in both risk and CISC can I run, or like a risk compatible code will not run in CISC, or CISC compatible code not run in risk? Is there any such differences?
No, sir.
Ideally, risk and CISC can run any code. It is intercompatible, right? But the challenge is in risk, I have less number of computation engines, less number of instructions. So let's say I don't have multiplication. I have only adder and subtraction. So how does risk achieves this multiplication? It could be by repeated addition or through some shifting operations, right? So now this has to be identified somewhere, right? So these instructions has to be identified somewhere. So who will decide these instructions? Continuous addition should happen, continuous shifting should happen. Who will decide? It will be decided by whom? Compiler. So in case of risk, it is a compiler intensive. So compiler will have more work to fit that entire thing in the existing instructions. Whereas CISC, it is not a compiler intensive. Compiler will be easy because for everything it has one hardware. So it need not think about like, okay, I need to, how do I add because I don't have hardware? How do I multiply because I don't have hardware? So those kind of uh, computations or optimization CISC need not do, right? So that is the one of the advantage. Okay. So currently, when I say early system used simple 8-bit microcontroller with the 8051 or PIC, those are x86. Still, there is x86 from Intel. Same way, it has a transition to 32-bit microcontrollers, that is ARM series. So that is RISC architecture. So now high performance computing, even not even 64, it goes up to 128 bits also. Okay. Now the systems are no more just embedded systems, right? So now the systems are more on a computing systems, like it can be IoT system, cloud computing system, AI systems, right? We talk about systems rather than just a simple embedded controllers, together with the cloud integrations, all these aspects. Okay. So all our modern electronic systems, right? It depends on embedded systems. I can give you some examples. Whether my mobile phone relies on embedded systems? Yes or no? Hello? I'll give you,
Yes, sir.
I'll ask some questions. So whether my smartwatch relies on embedded systems? Yes or no?
Yes, sir.
Whether lift what you travel, whether it depends on embedded systems?
Yes, sir. It's different.
Leave aside the scooter, bike, car, whatever you use, wherever you go, you need embedded systems, right? So
Yes, sir.
any system, any current systems you take, it requires embedded systems. Okay. So whenever I see, like, I mean, as a company or product, whenever I design embedded systems, I have to go for low cost, real time, compact in size. So who will take a huge, big mobile phone, right? It should be compact in size. It should be reliable. It should be scalable, right? And it should be interoperable. When I talk about interoperable, what do you mean by interoperable? You can take an example of software interoperability. So can you give me an example of software interoperability? What do you mean by interoperable? So let's say a Linux operating system. So irrespective of it is Lenovo PC, Samsung PC or anything, it will run that Linux PC, right? So same way, your embedded system, what you design, irrespective of the architecture, x86, CISC, RISC, anything, so your software should run anywhere, right? That is very much needed. Interoperability. Okay. And another thing, the overall systems, right? Embedded systems, it should be low power consumption. It should have low power consumption that we already discussed. And another important thing, it should have memory and processing resources. Okay.
Yes, sir.
So this architecture we already discussed. We need CPU as a central processing unit. And one important thing I missed when I was discussing about syllabus, so memory, right? So any embedded system, you need to have RAM, to store the data, you need flash, right? Then we need to talk about input output peripherals like the sensors, right? Then whether my embedded system works without clock, it
No,
is a sequence of operations, right? Clock by clock, sequence of operation. So we need to have clock. Then we need to have reset circuitry, and we also have UART, SPI to CCAN, ARINC. All these interfaces in detail we'll be discussing in our embedded system. Okay. So as we know, like embedded systems, there will be base SoC. In our case, we'll be talking about STM32. To that STM32, there will be memory, peripherals, sensors, connectors. Then on top of that, we will have device drivers. Device driver is like a middleman who will be talking between your software and these peripherals like UART, I2C, SPI. It will be talking between these two, right? Then to run all these things, you need operating system, right? In terms of operating system, we'll be discussing about Linux. And in the Linux also, we'll be discussing about Zephyr and real-time operating system. Then on top of that, we'll have middleware and then application. Okay. So there are types of embedded systems. One is independent standalone embedded system. When I talk about independent standalone embedded system, like microphone or calculator, do I have any deadline to respond? No, right? So for given task, if it is performing, that is fine. You don't have any deadline. But in case of ADAS, or in case of uh, like airbag, right? So it should respond within a given deadline. It should be a quick, right? So that is real-time systems. Okay. So we have various types of embedded systems. Connected network, like smart meter. Smart meter nowadays, like all your electric meter, water meter are like actually connected to cloud, right? These are all connected networks, right? Routers. In healthcare application, we use embedded systems. So it should be real time. So I'll be just going a little faster, just since it is just an overview class. So we will have deadline based execution task and priority based execution task. It's real time, as I mentioned, like especially for the real time applications like airbag systems. We need to running some. We are running some kind of RTOS. Okay. So, but when I design any embedded system, it should be power consumption limitations. As I mentioned, as a mobile, I cannot have like 2 days, 3 days, I mean, 2 hour to 3 hour backups. So I need to have longer backups. So power constraint is very much needed. Cost is very much important. When I design, I cannot design with like ultra scale FPGA embedded system, because if I use ultra scale FPGA based embedded system, it costs in lakhs. Let's say just for the fire alarm, people will prefer maybe like 5 to 10,000 rupees. So what application you use, accordingly you have to choose the component, it will meet that pricing. But let's say like for the space application, even if I spend 2 to 3 crore, it's still fine. Okay. Then thermal limitations. So whatever the embedded system I build, it should work in Himachal also, in Bangalore also. When I go to the negative temperature, your embedded system shouldn't be stop working, right? So the same thing falls under temperature, humidity, and dust. Okay. And whenever we design any embedded system, certification is very important. Let's say like if you are designing one automotive system, there are various bodies which will certify your system, right? So you should understand that. So this also very briefly we discussed. Any microcontroller, we have internal CPU, we have flash memory for storing the data, SRAM for data, real-time computation. We have GPIO ports, right? So why do we need GPIO ports? To connect external LEDs, external motors. We have timers, counters, ADC, DAC, right? So we'll discuss all these aspects in actual sessions. So this is like generic architecture, right? You have CPU, then all the memory aspects, then interrupt controller, clock, ADC, DMA. What do you mean by DMA? Direct memory access, right? So let's say like you have one memory, your processor is running, and you are getting real-time data. Now, if you want to read the real-time data and then write to this memory, so you have to waste some clock cycle in the processor. It will be wasting your processor cycles, right? So what people will do, they will use something called DMA engine. So you just need to tell the DMA that like whatever the data I'm receiving, directly write to memory. So processor shouldn't need not be stopping. So it will be continuing its own work. So parallelly, it will be writing everything here, right? So what is the difference between microcontroller, microprocessor, and FPGA? So microcontroller is something like you have a processor along with all the peripherals like UART, I2C, SPI, GPIO, all these things. Whereas microprocessor is mostly the processor, but processor itself can be multiple, like 2 core, 3 core processors. It is computation intensive task, right? And like if you want to run an operating system, you don't prefer microcontroller unit, you prefer microprocessor unit. Okay. FPGA is something like it when you want to have parallel processing. It follows something called lookup table concept. So this FPGA we will discuss in detail when during our sessions. So it will have something called lookup table. If you want to build some kind of fast GPU, high speed computation for artificial intelligence, then you have to go for FPGA based systems. Okay. So generally in embedded systems, you will have bootloader. It says, see, your program is stored in some memory, right? So somebody has to tell your microcontroller from where you have to read the data, right? So that will be taken care by bootloader. Then on top of that, we'll be running real-time operating systems like Zephyr, FreeRTOS, where you will be running your real-time tasks. Okay. Then there will be middleware for communication, like if you want to write I2C, UART, all these things, you'll be using middleware. Then there will be application layer for user logic. So application layer is something like you are writing something like, let's say, LED blinking, which you have written. So that falls under application layer. Okay. So ideally, in RTOS concept, what we'll be discussing is like we'll be discussing how do you write shared memory, how do you deal with mutex, how do you deal with ISR, right? How do you write your own kernel? So this is very important. It has a lot of demand. Basically, if you understand this RTOS concept, right? So the companies like Bosch, Schneider, Continental, many companies, right? Hyundai. So all these guys are like behind these RTOS experts. So power management techniques you especially need for ultra low power devices like your mobile application, or let's say IoT application which you might have deployed across the field. So you need these power management techniques. Okay. So then important thing we have to understand is debugging techniques. So once you design your own system, how do you debug your system is also very much important, right? So all these aspects we'll be discussing in debugging system. Okay. So then in introduction to IoT system, we'll be discussing about how do you connect the network, machine to machine communication, especially for industrial automation. Okay. And now everything is AI integrated, right? How do you add AI analytics to it in industrial automation? Okay. So now you know what is the architecture of simple embedded system. Along with that, when you add gateways, protocol, cloud, web application, then it goes for IoT system, right? You can see here Raspberry Pi or Arduino, all this will be edge node. Then TCP/IP, it will be communicating to the cloud. Okay, so we'll be having gateways also. So various IoT communication protocols are there. All these we'll be discussing in detail, like satellite communication protocol in terms of Wi-Fi, Bluetooth, NFC, right? So there are various modes: device to device, device to cloud, device to gateway, and hybrid communication models. So let's say like one example, if I want to give you. So like we are working with the one ocean project. So in ocean, directly from the center of ocean, we will not be able to fetch the data, right? We have deployed around 2000 units of sensor nodes in the ocean. So each nodes will be communicating each other, and it is forming one network, and then it is sharing to us. Okay, so this kind of hybrid protocols are required, or sensor network we call it as. Okay, these are the sensor network, the communication protocol what we'll be discussing in detail: Wi-Fi, Bluetooth, LoRa, cellular, etc. Okay, and one of the important protocol with respect to IoT is MQTT. Okay, then we'll be discussing HTTP, COAP, COS, right? So all this aspect we'll be discussing. Okay, and let's say like if you want to now you talk about edge, right? How do you deal with building your own edge computer? So that aspect we will discuss in this particular part. Okay, then finally once you design anything, security is important thing. How do you deal with these securities? So nobody should attack. Let's say like you have implemented one IoT node, or like I was talking about ocean nodes. So if someone like hack it and destroy like 10 nodes out of it, like thousands of nodes what we deployed, So my entire network will be disrupted. So how do I actually save from those attacks? Okay, so various things are there. Like if you see here, lot of things are connected to cloud. So how do you secure it? Okay, so industrial IoT is also one of the booming field. So in any manufacturing sector, how do you integrate this embedded system and automate? And agriculture, how do you automate? Healthcare, how do you automate? Okay, then I was talking about, we talk about tiny ML. So we'll be running ML on top of microcontroller itself. So those aspects also we'll be dealing. So what skills you need to have as an embedded engineer? So basic is embedded C, C++, embedded Linux you should know, networking protocol, cloud APIs you should understand. And some, I was telling, like you need to understand some basics of hardware also. That is very much needed. Okay. So those aspects we'll be discussing in detail, like data sheet reading skills. How do you appreciate a schematic, right? So then you are not just a designer, right? So whatever the design you have done, you have to debug. So your design, somebody else will not debug. If you have made mistake, you have to debug, right? So those aspects also you should see. So general career role, right? You'll have firmware engineer, embedded Linux engineer, IoT solution engineer, hardware validation engineer, system integration engineer, embedded designer engineer, right? So various roles are there as a embedded engineers. Okay. So these are some of the mini project ideas which we'll be discussing also. I mean, these are like you can say stage one project, but stage two, stage three, we'll be dealing with some satellite communication application, defense projects. So which as a problem statement which I have got. So those problem statement we'll be discussing. Okay, so that's all actually about, like, I mean, I just wanted to show you the brief of overview of like whatever the initial discussion I mentioned, right? The slide where like I mentioned the flow what we'll be studying, and here I just wanted to show you that like what in detail what we'll be going through, right? So now if you have any questions you can ask, then like we can conclude the session and like we can meet from next week onwards in the actual session. Okay, so any questions so far?
Sir, is this training fully online or off? Will be offline, online, offline, so both,
I
sir?
think it's a hybrid. You can just check with the institute on this part also. Okay.
Okay, sir.
Any other question?
Sir,
Yeah.
sir, previously you had said that for writing the code we have to note the clock cycle, that optimization. If the clock cycle increases, the power or hardware that increases, or it doesn't matter.
No, as the number of clock cycle increases, power increases, right? So we have to optimize. So there is always trade-off, like how many clock cycle you use and how do you deal with that. As the clock cycle increases, your power obviously goes high.
Yeah, okay. As an embedded engineer, our role is to develop the device driver, right, sir? So for that embedded, we can use embedded C or C++, or we can use other languages.
Other languages also, Python, right? C++.
Yeah, okay. So we are OS developing, it comes under embedded or other. It's a
OS,
software.
embedded operating system, driver device development, it comes under embedded itself. We'll be discussing that also, embedded device drivers.
Yeah, okay, thanks.
Anything else? Okay, then we'll meet in the classroom. Thank you.
Thank you, sir.